Okay, let's see. Blah, 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 blah. Okay, so, so on Friday, I'll release a, probably like a take-home exam, okay? So take-home exam on Friday. I don't know, I feel like maybe I'm making this too easy for you guys. Okay. Well, when you fill out your evaluations, don't tell them I made the class too easy then, okay? Say it was the right, appropriate amount of difficulty. Huh? Yeah, and speak highly of me. Let them know that that you enjoyed my class, okay? Please, please. Extravagant sounds a little funny, but anyway, okay. So there's going to be a handwritten component, okay? And you know, because there's a handwritten component, I was debating still just keeping it in class. But okay, so the handwritten component will be, you know, I'll probably give you a small grid of data, okay? Small matrix of data. Okay, and then I will ask you to calculate things by hand. So you show your work for all of these things, and you know, so probably find the covariance. Oh, or here, let's reverse. Okay, so small matrix of data, and then we'll basically just do kind of this a little bit of PCA manually. So you'll center X, and then you'll find the covariance of you know, your centered X, which is basically just what, X transpose X or XX transpose? I always get these mixed up. One of these. XX transpose? No, X transpose X. Sorry. Yeah. Okay. Okay. What? Yeah. Okay. So you center your X, and then you know, find your covariance, and then you're gonna do you know, your spectral decomposition or eigen decomposition. Okay, and then re-express X in principal components. Okay. And I think this is very doable. You know, if I give you something like a 2x4 or 2x5 matrix, or not 4x2 or 5x2 matrix, something, just a small data set, I think it's very doable. Okay? And so, of course, show all of your work for the grader. And then because it's at home, you can always double check your work against the computer. So, but whatever, okay. And then, so you'll have that handwritten component, and then I'll probably do a PCA regression, just a small, I'll walk you guys through it, okay. PCA regression task. And I guess I'm assuming everybody is at least familiar with some concepts from linear regression when I assign PCA regression here, okay? All right, so I'm writing this up, and I'll get it posted on Friday. Yes?
When will it be due?
Yeah, probably like Monday, okay? So I'll post it Friday, like immediately after class, and then I'll probably do Monday like 11:55 p.m. Okay, so because I'm always confused on, I think, like if I said Monday on CCLE, if I say Monday midnight, it ends up being like Monday at 12:01 a.m. and so it's like it's really just Sunday night. So I always say. To be unambiguous, I always like to say like 11:59 or 12:01 because I think that So, but they only do 5-minute increments. Well, anyway, okay. So, what's up?
Towards the end of the day Monday.
Yeah, end of day Monday. Okay. 11:55 p.m. Okay, and that way you'll at least go to sleep after midnight, right? Because if I said Tuesday morning, 3 a.m., I guarantee I'll get submissions at 2:59 a.m. So, okay, it shouldn't be too bad. So, well, okay, well, let's see. Oh, how am I going to do this? Okay, so the PCA regression task, I'm going to have to split this into 2 parts because the handwritten part you have to turn in by hand. Okay, so this will be due in class Monday. Is that okay? Due in class Monday, so that would be what, 2 p.m.? All right, and then the PCA regression task will be Monday, 11:55 p.m. And then, you know, the internet is available, but do not talk to each other. Okay? Do not discuss with classmates. And this is on the honor system here. Okay? My OneDrive, OneDrive is like freaking out on me, and like all of my files disappeared. They're still up in the cloud, but they disappeared off of my own computer. So I'm hoping everything's okay. I'll be really sad if they also disappear off the cloud. I don't know what the ruling is there. Okay. All right, so that's that'll be a midterm exam, and then yeah, okay. So now we'll start. We'll move on to our next topic, which is optimization. Okay. Is somebody excited about this? All right. Okay. Well, everybody should be excited. I mean, it's optimization. This is okay. All right. So optimization. At its kind of the basic idea is, you know, you've got some kind of function and you're trying to find either a minimum or a maximum, okay? Have a function and we want to find a, you know, minimum or a maximum. And there are, if you go onto Wikipedia and you look up mathematical optimization, they're going to have like 50 different methods. Maybe, I don't know about 50, but there are lots, okay? So we're not going to be able to cover all of these. We're going to just cover a few, like, so all of these are major subfields of optimization, okay? And then these are some iterative methods and optimization algorithms, all of these different things, okay? And I think last quarter, if you were in my 102A class, I just talked about this Nelder-Mead simplex algorithm, where you just take a triangle or, you know, a simplex and all of this, and look at all of this. This is all under the topic of optimization stuff, okay? Oh my gosh, okay. Well, anyway, so we're just going to cover just a couple of these basic things, okay? And so we'll start off with gradient-based optimization, okay? And so I guess we'll have to define a few things like the gradient and all of this, and maybe some of you're already familiar with a lot of these things, but we'll go through a little bit semi-formal. So this is not 100B, so I'm not going to be super formal about all of my proofs and definitions, but we'll be semi-formal, all right? Okay. And then, so a lot of times, you're trying to find a minimum or a maximum. Some of these algorithms only work for finding a minimum or finding a maximum or something. So a lot of times, if you're trying to maximize a function, but your algorithm only works for a minimum, all you do is you just apply a negative to it, and then you find the minimum of that, and that will be the same as your maximum point. Okay. You've got all sorts of applications. So you have like maximum likelihood estimation is all about optimization. Okay. What's that? Okay. So just some applications. There are tons of applications. Okay. So maximum likelihood estimation. This is just so you've got you have a likelihood function and you're trying to maximize it. Okay, so that's an optimization, right? So have a likelihood function, and then you find the parameters that maximize it. A lot of machine learning things. Okay, so and again, machine learning is just a huge subfield that you can do all sorts of stuff. Okay, so a lot of machine learning, especially if you're doing like supervised learning. Okay, so or even unsupervised learning. Okay, so with machine learning, let's say you got some kind of supervised learning. Supervised learning means you are you have some inputs and you have known outputs for those inputs. Okay, so like linear regression is a very basic form of supervised learning. You've got some X inputs, you've got some known Y outputs associated with each of those X's, and you're trying to find a function that optimizes something there. Okay, so under supervised learning, I guess linear regression falls under this. Okay. What is the function that we're trying to optimize in linear regression? The function that we're trying to optimize. What's that? So we're taking, we are searching for the function that we're optimizing is the sum of squares residuals. Okay, so you have the function which is the sum of squares residuals. And you're trying to find, the betas, beta hats, that minimize this function. Okay, and so linear regression, at least for ordinary least squares regression with two variables or whatever, it's a solved problem. Okay, like we don't need to plug it into an algorithm and say, hey, try to minimize this thing. It's already been solved. We know that beta, the slope beta 1 hat is, correlation times sy over sx. Okay, so that's already solved. But in a sense, it's still an optimization problem. Okay, but you can have like artificial neural networks with some kind of which is just this fancy term for weighted things. You got okay, and you've got some kind of you've got parameters here. You got you're trying to minimize a loss function. Okay, minimize the loss function, and then, you know, so you, based on adjusting the weight parameters, okay? So anyway, lots of applications for optimization. Yes?
So wouldn't PCA be considered a form of optimization? You're trying to, I guess, like, when you're doing that.
Okay, yeah. Yeah, so PCA, you're trying to maximize the covariance, or the variance, and zero out the covariance. I guess it could be seen as an optimization problem, although it is, quote, solved in the sense that we know that the eigenvalues, eigenvectors are gonna perform this. So there's no, there's kind of like no search that we have to be performing here. Okay, so gradient-based optimization. This is basically the multivariate generalization of, in calculus, you guys found local minimums and local maximums based on the derivative, okay? So the gradient, so let's just, yeah, okay, let me write this, okay? So this is the multivariate generalization finding local minima / maxima based on derivatives. All right, so let's save this. Okay. All right, so let's so we'll just go back and to what we learned in calculus. Okay, so we'll talk about, you know, so univariate derivatives. All right. Do you guys remember the definition of a derivative? So, you know, if f is some function, f of x is some function of x, okay? And I guess we can say f maps from the real space to the real space, okay? Okay, so the derivative of f, okay, so this is f of x will be first derivative of x which we can say is df dx, okay. Here we'll say the derivative of f at x0, so df dx, where x is equal to x0. What is this? How do we define this? Okay, rate of change. So what do? We say, so if we draw a picture here, okay. So if this is x and this is f of x, okay. And we can say here is x0, and then we've got some function here. Right? We want to find the this thing, right? So what do? We add a little delta x. So we have x0 plus delta x, and then we evaluate the function at f of x0, and then we also evaluate it at f of x0 plus delta x, yeah? Okay, and then so our derivative is basically the limit as delta x goes to 0 of the difference between all of this, I guess. So, I don't know, maybe I should draw the... Okay, so we've got f of x0 plus delta x minus f of x0 divided by delta x as this goes to 0. Okay, and then we got nice little power rules that tell us, like, when you have x squared, it turns into 2x and things like that. Okay, we could yeah, okay. It's the tangential line. Okay, so we could define some angle alpha here also, and then the derivative would be equal to the tangential line. Okay, but anyway. So this is so that's for the univariate case. All right, the multivariate case. Now that we're going to deal with vectors. So instead of single values of x, we've got a vector, and this is called the gradient. Okay, so the gradient is the derivative with respect to a vector. Okay. All right, and so here the our function f maps from n-dimensional space to one-dimensional space. Okay, so we've got, so our x is n-dimensional. Okay, and then our output is scalar. Okay, so x all right, so so we define the gradient of f. Okay. At x is, okay, this is our symbol for the gradient of f. Okay. And it's basically the partial derivative of the function with respect to each term in x. So it's the derivative of f with respect to x1 okay. So so the derivative, okay, the derivative, or not the derivative, the gradient is in n space also. Okay, so our gradient is n-dimensional. Okay, and then so for any one of these, okay, any one of these terms, okay, so the derivative with respect, let's say we want to find what is, df dx2, okay, or the partial derivative of that. This is this would be the function evaluated at x1, and then at xi plus delta xi, but then just evaluate it because it's a partial, right? So we're only modifying the xi term, okay? And then we're just subtracting off f of x. So this is, x1 okay, so this is just the term evaluated at the current x, right, over basically delta x, x sub I. Do I have to put this as a limit? Okay, so but again, generally you don't have to worry about doing these limit operation type things. Okay, so we can just use like power rules and for whatever. Okay, so here's we'll do an example. Okay, if let's say our function f of x it's a function of x1 and x2. So it's x1 plus x1, x2 squared, okay, where, I guess we can say element of two-dimensional space, okay, and we can ask, what is the gradient of f, and what is gradient of f at 1, 1. Okay, so we'll do our gradient of f. Okay, so remember our resulting gradient is going to be a two-dimensional vector. Okay. All right. So what is this with what is the derivative of this with respect to x1? So partial derivative with respect to x1. This would just be what? 2x1 plus, and then this is basically just a constant here, so it just becomes x2 squared, right? And then what is this thing with respect to x2? Okay, well this disappears because that's just a constant, and this power rule we say it's 2x1 x2. Yeah. So far so good. Okay, and then so if we want to evaluate this at the location 1, 1, we just plug in 1 and 1, and we get 2 plus 1, so we get 3, 2. Is that right? Gradients? Okay, it's just that. Okay, we can maybe geometric interpretation. Okay, so here I'm going to draw out this will be x1 and x2, okay? And then our function, you can imagine just having some kind of contour. Okay, so this is the contours Okay, and so if you've got some location x, okay, so x is the point x1 and x2. Okay, you can have basically the this is delta x1, okay, and you would have a delta x2, okay, and so this takes us over to the point x plus delta x1 x2, and this would take us over to x plus delta x1 comma x2 plus delta x2. And essentially, so our resulting, the difference between x and the resulting location of, this is this spot right here would be basically x plus delta x, right? Is this spot right here? No, I don't know. I don't want to write that. Okay, so this is and effectively, what is the difference between the value here and the value here? And maybe I didn't draw my, probably drew my thing. They should be at kind of like different contours, and basically the height difference, if you're imagining this to be like a contour map, what's the height difference from here to here as we shrink delta x down to 0? That's going to be the gradient, okay? So the gradient is, so there's a f of x, and then we've got f of x plus delta x. What is the difference between these values, okay? Difference between these values, okay, and then, so how does our slope change as we shrink delta x to 0, okay? And so what we can see is that, as we look at the gradients, or the gradient around a certain point here, okay, the gradient will give us the direction of steepest ascent or steepest descent, okay? Okay, and okay. All right, so we've got, so a few properties, so additional properties. Okay, so the first one is the gradient point X gives us the direction of the steepest slope. Okay, all right. Maybe I should. Point X will be a vector. Pointing in the direction of the steepest slope. Okay, and then, you know, so if we have, you know, in two-dimensional space, let's say we have f of x1 star and x2 star equal to a constant. Okay, so then x1 star and x2 star would then be basically a contour line, right? Okay, and we'll say vector v is a tangent vector of the contour. At point x equal to x1, x2. Okay, and then so what we will find is that the inner product of the gradient x1 star and x2 star, or I guess it would just be x1, x2, the gradient of x1 and x2 and our vector v, what is the inner product going to be here? So v is the vector that's tangent, okay? And this is the direction of steepest slope. Yeah, this is going to be 0, okay? Because we've got, basically we've got, you know, some kind of contour here, right? And then we've got a vector tangent at point x. This is v, okay? And then our gradient is going to be this direction over here. And so the inner product there is going to be 0, okay? So I mean, basically that means the tangent vectors, the vectors tangent to a contour are perpendicular to the gradient at that contour plot, or at that point, okay? So, vectors tangent to a contour are perpendicular to the gradient at that point. Okay. I think that's all right. I'm going to run out of time here. Okay. Well, I guess I'll just mention, and then we'll talk about it a little bit more in depth on Wednesday. Will be the Hessian. Okay. I don't know why they come up with all these names here, but so you have the first derivative. Okay. The first derivative, the multivariate equivalent, is the gradient. the second derivative, the multivariate equivalent of that is the Hessian, okay? Well, what's going to happen? All right, so the Hessian, all right, so let me just say first derivative basically turns into the gradient, which is a vector. And then the second derivative turns into the Hessian, which will be a matrix, okay? And that's because, well, I'll show you guys on Wednesday. But the gradient is a vector, the Hessian will be a matrix. It's the second order derivative, basically. All right, we'll see you guys in a couple days.